All right, guys, last time we looked at some graphs, we saw a position versus time graph of this car moving back and forth, and it looked really abnormal, really jerky and not realistic. And the reason was because we had changes in velocity that were instantaneous. And in real world settings, that doesn't really happen. We have changes in velocity, but they happen over the course of time. And that's what we call an acceleration. An acceleration is defined as a change in velocity. In physics, it has a much broader term than it does in normal conversation. In normal conversation, we say acceleration and we mean speeding up. But in physics, when you talk about accelerations, that just means changing velocity. And since velocity consists of speed and direction, that means you're changing speed or you're changing direction. And it doesn't have to be speeding up, it can be slowing down, and it can be reversing direction. When in the case of one-dimensional motion, it's going one way or the other. In the case of two-dimensional motion, it could be going around a turn or something like that. But since we're in one-dimensional motion, it's going in a positive direction, then a negative direction, and that's undergone acceleration, even if the speed stays the same. So that's what we saw with the last motion of the car. It went one direction and then the opposite direction at the same speed and jerked around and stuff. So we have a much more realistic look at this car, and you can see it speeds up and slows down, sits for a moment, then speeds up and slows down backward. And we get this graph of position versus time on the top here that is much more curved. So whenever you see a curve, that means the velocity is changing. So it's speeding up or it's slowing down, and that's what we see in the first two sections of time. We see the velocity versus time graph that then has diagonal lines. And when a velocity versus time graph has diagonal lines, below that, the acceleration versus time graph has a non-zero constant value. So the first section of time, we have a positive acceleration of a constant for that first second and a half of time. And then we have a diagonal line that tells us that the velocity is changing at a constant rate. That means it's accelerating. And then we have a curve above that. So much more realistic look. If you watch the car move, it smoothly moves and then smoothly speeds up and slows down. So that's why we get a much more realistic look at the car, at its motion, and we get a curved position versus time, because acceleration does take time. It can't happen instantaneously. So that's what we're looking at today when we talk about acceleration. So accelerations have to be shown by having a curve on the position graph, but the position graph doesn't give us a way to really calculate the acceleration. So that's why the velocity versus time graph is really handy, because the velocity versus time graph gives us a way to find the acceleration because it has a constant slope. And the slope for that graph tells us what the acceleration is. So whenever we have a diagonal line on a velocity versus time graph, we have a measurable acceleration. And the position versus time graph is going to be a curve. So the velocity time graph is really helpful for us in that sense. All right, so let's take a look at this slide. Here's a velocity versus time graph with a straight line that's diagonally sloped. It's got a negative slope, which means it's got a negative acceleration. That doesn't mean it's slowing down. It doesn't mean it's speeding up. It could be doing both. And in fact, this one is doing both. A negative acceleration just tells us how and in what direction the velocity is changing in. So if we take one sentence to talk about what's happening here, an object going at 10 meters per second changes its velocity to negative 10 meters per second in 10 seconds. That's one sentence. Now, if we wanted to explain further, we would have to talk about how it actually reverses direction and what's going on there. We could also talk about it numerically and mathematically. So the slope of this graph is the acceleration. So we could say the object going at 10 meters per second accelerates at a certain rate for 10 seconds because the slope of the graph is constant. And to find that slope, we would just take the rise divided by the run. The rise is the change in vertical on this, and so that'd be negative 10 minus 10, so negative 20 meters per second, that's the change in velocity, divided by the change in time, which is 10 seconds. So negative 20 meters per 10 seconds, or negative 2 meters per second. And so that's what we're looking at in terms of acceleration. So we can say an object moving at 10 meters per second in the positive direction experiences an acceleration of negative 20 meters per second, negative 2 meters per second for 10 seconds. And it should end up at negative 10 meters per second. So that means that after 1 second of moving, it's going 8 meters per second. After 2 seconds, it's moving 6 meters per second. After 3 seconds, it's moving 4 meters per second, and so on until it reaches a velocity of negative 10 meters per second. All right. So what's happening at this spot? Well, at that spot, it's not moving for an instant in time. That does not mean it's not accelerating. Because the acceleration is a slope, and that line obviously has a slope. That means it's changing direction. So up until that point, it was going in the positive direction, but now that instant, it's stationary in the midst of a direction change. So now it starts going backward and speeding up. So we can't say over the 10 seconds that this is slowing down or speeding up because it's doing both. So we have to be aware of that. If we look at the times that are marked, the 4 seconds and the 9 seconds, when is it going faster? Well, it's going faster when it's farther away from the axis. So at 4 seconds, it's actually going 2 meters per second in the forward direction or the positive direction. At 9 seconds, it's going negative 8 meters per second. So it's actually going faster at that point, but it's going in the opposite direction. So there's a lot of information we can get from these types of graphs. These graphs tell us the velocity, the acceleration, and the displacement. The velocity is simply the value on the graph. Where is it on the y-axis? The acceleration is the slope, and it's important to indicate whether it's positive or negative because that tells us how the velocity is changing. The displacement, how far it's gone and in what direction it's gone, is also findable. And that's because if we find the area under the curve, that gives us the displacement. What we don't have on this graph is where the object is that's being graphed. The velocity versus time graph doesn't tell us where it is. We can tell how far away it's gone and in what direction, but we don't know where it started. So that's something that we lose in this type of graph. So we would need a position versus time graph for that information. So if we look at each of these scenarios, we can talk about each of them. The acceleration on the first one is 0 because our slope is 0. So it's maintaining constant velocity. If it's going at 4 meters per second for 15 seconds, that means it's gone 60 meters. And that's the area of that rectangle. 15 seconds times 4 meters per second is 60 meters. And the area of that rectangle is 60. The next one here is accelerating positively. It's going from rest to 6 meters per second after 15 seconds. So it's got a positive acceleration, and that's because of the slope. So if we find the slope, we would take the change in velocity, 6 meters per second, divided by the time, 15 seconds. And I believe that's going to be 0.4 meters per second. I forget exactly. But then to find the area under this, obviously it's not a rectangle. So we have to use a triangle formula, 1/2 base times height. Well, our base is 15 seconds. Our height is 6 meters per second. And we multiply those two together and multiply it by 1/2. So 1/2 of 6 is 3. 3 meters per second times 15 seconds is 45 meters. So we get 0.4 meters per second, and that's positive because it's got a positive slope. And in that time that it takes to speed up to that velocity, it moves 45 meters. The third graph here, it is moving from 4 meters per second to rest, to come to a stop at a constant rate. So it's got a negative acceleration, but it's still got a positive velocity. It's still moving in a positive direction. but it eventually comes to rest. So the question would be, how far does the object go as it comes to a stop from 4 meters per second in 15 seconds? That would be a problem this would solve. So we can find the acceleration rate. The acceleration rate is negative 4 meters per second divided by 15 seconds. I believe that's 0.27, the magnitude of that. So it'd be negative 0.27 meters per second. So every second its velocity changes 0.27 meters per second in the negative direction. And then the area would be 1/2 base times height. So 1/2 times 4 meters per second. So that's 2 meters per second times 15 seconds. So 2 times 15 is 30 meters. So we get those two values on that. So anytime we have that. Now, if we have a corner or something, we have to break that up into parts. So we can't do this unless we have a constant diagonal line. And if we don't have a constant diagonal line, then we've got to break it up into parts that we can find the area of for the displacement. So we have these different measurable values that really tell us where an object is, how fast it's going, what's happening, how long it's taking. And those are the 5 variables that we always want to be able to figure out. So when we start doing formulas, the 5 variables that we're going to use are displacement, and generally we measure that in meters, that's our base unit. The velocity, both when it starts and when it stops. We're not as concerned about the velocity in between, except for the fact that we want it to have a constant acceleration. So usually we're looking at constant acceleration situations, and acceleration is measured in meters per second, or meters per second squared, as you see on the screen. And then the time. The time is the one thing that ties it all together, because the time doesn't change. It stays the same and keeps going forward. So these are the 5 variables that we're going to be using as we start learning about formulas and how to use them, and those will be coming up in the videos to come. So every time we do a problem, I want you to get in the habit of listing out these 5 variables, because when we read a situation, we're going to have to say, okay, how much has it changed its position? What velocity did it start at? What velocity did it end at? And if we know all of these different things, we can calculate the other ones. All right, that's where I'm going to stop here today. So have a great rest of the week, and I'll talk to you guys later. Thanks.